Module 1, Unit 1, Introduction to Earth Science. Earth science is a fascinating field that seeks to understand our planet's physical characteristics, processes, and systems. It is an integrative science that examines Earth's structure, its history, and the dynamic interactions within its atmosphere, hydrosphere, lithosphere, and biosphere. To truly appreciate Earth science, one must delve into its foundational concepts, which include understanding Earth's formation, structure, scientific methodologies, and the fundamental principles governing natural phenomena. Gravity, a fundamental force in the universe, extends its influence far beyond Earth's spheres and plays a pivotal role in the formation of galaxies. By drawing together matter, gravity clusters stars, gas, and dust into the immense structures that define the cosmos. This force not only organizes the material within galaxies, but also governs their motions and interactions, shaping the vast, dynamic universe we observe today. Its reach underscores the interconnectedness of all celestial and planetary systems, reminding us that Earth is part of a much larger cosmic framework. The primary force responsible for the formation of galaxies is gravity. This fundamental force attracts matter together, leading to the clustering of stars, gas, and dust into galaxies. Gravity ensures the cohesion of these celestial bodies and orchestrates their motions, forming the complex structures we observe in the universe today. Central to Earth science is the process of scientific inquiry, a structured approach to answering questions and solving problems. The scientific method begins with observation, a crucial step that involves gathering information through the senses or instruments. For example, when you enter a dark room and the light does not come on after flipping the switch, several hypotheses can be formulated. Perhaps the bulb is burnt out, the switch is faulty, or the power supply is disrupted. Each hypothesis can then be tested systematically. If replacing the bulb does not resolve the issue, the fault may lie in the switch or power connection. This iterative process exemplifies how science progresses through testing and refining ideas until a robust explanation emerges. As observations accumulate, scientists develop hypotheses, tentative explanations for phenomena. For example, a hypothesis might suggest that applying starch to fabric prevents wrinkling. This hypothesis would need rigorous testing, including controlled experiments where identical fabrics are treated with and without starch and subjected to the same conditions. Observing consistent outcomes over repeated trials would lend credibility to the hypothesis. With sufficient evidence, a hypothesis can evolve into a theory, a well-tested and widely accepted explanation, much like the theory of plate tectonics, which revolutionized our understanding of Earth's dynamic crust. The theory of plate tectonics illustrates the power of scientific theories to explain natural processes. Among these processes are the movements along faults, which are fractures in Earth's crust, where blocks of rock move relative to each other. Strike-slip faults are particularly significant, as they are associated with horizontal motion caused by lateral forces. These faults, such as the infamous San Andreas Fault in California, occur where tectonic plates slide past one another, resulting in powerful earthquakes and dramatic shifts in the landscape. Observing the behavior of strike-slip faults provides crucial insights into the mechanisms of plate tectonics and their role in shaping Earth's crust. Evidence supporting this theory includes the distribution of earthquakes, volcanic activity, and the alignment of magnetic stripes on the ocean floor, which reveal patterns of seafloor spreading. Earth's structure is another foundational concept in earth science. From its center outward, Earth consists of the inner core, outer core, mantle, and crust. The inner core, composed primarily of iron and nickel, remains solid due to immense pressure, despite its extreme temperature. Surrounding it, the outer core is liquid, generating Earth's magnetic field through convective movements of molten metal. Above the core lies the mantle, a region of silicate rock that flows slowly, driving plate tectonics. Finally, the thin, brittle crust forms Earth's surface supporting all terrestrial life. The thinnest layer, the crust, plays a critical role in earth science. It is here that rocks and minerals are formed, weathered, and transformed. Rocks classified as igneous, sedimentary, or metamorphic undergo a continuous cycle driven by geological forces. For instance, igneous rocks form when magma cools, either below the surface as plutonic rocks or above as volcanic rocks. Over time, these rocks can break down through mechanical or chemical weathering, with physical forces like frost wedging expanding cracks in bedrock. Eroded materials are transported by wind, water, or ice, eventually settling to form sedimentary rocks. Under pressure and heat, these rocks can metamorphose, completing the cycle. Beyond rocks and minerals, Earth's dynamic processes shape its surface and influence life. Weathering, soil formation, and erosion are particularly significant in understanding landscape evolution. For example, in moist, temperate climates, frost wedging is highly effective, while chemical weathering dominates in warm, humid regions. This relationship between climate and weathering highlights how external forces sculpt Earth's features over time. Water, essential for life, also plays a central role in Earth's processes. The hydrosphere, dominated by the vast reservoirs of oceans, participates in the hydrologic cycle, where water evaporates, condenses, precipitates, and returns to the ocean via runoff or infiltration. The moon also plays a vital role in Earth's natural systems, particularly in driving tidal cycles through its gravitational pull, which influences the movement of water and sediment in the hydrosphere. Its phases, resulting from its orbit around Earth, represent a complete cycle approximately every 29 days. This lunar cycle has been crucial not only for understanding celestial mechanics, but also for guiding ancient calendars and shaping cultural traditions worldwide. By observing the moon's consistent transitions, humans have gained insights into Earth's relationship with its closest celestial neighbor, further exemplifying the interconnectedness of Earth's systems and the cosmos. Understanding Earth's processes extends to the study of glaciers, deserts, and winds, which reveal the planet's diverse climates and landscapes. Glaciers carve U-shaped valleys, while deserts, though arid, exhibit features shaped by infrequent but powerful water flows. Wind, often credited with sculpting landscapes, primarily transports fine sediment, forming dunes and loess deposits. Earth's atmosphere, a thin layer of gases enveloping the planet, regulates climate and supports life. Composed mainly of nitrogen and oxygen, the atmosphere facilitates weather patterns and temperature regulation. Solar radiation, absorbed and re-emitted by atmospheric gases, drives the greenhouse effect, maintaining temperatures conducive to life. This delicate balance, however, is disrupted by human activities that increase greenhouse gas concentrations, contributing to global climate change. Efforts to mitigate this crisis include reducing reliance on fossil fuels and transitioning to renewable energy sources like solar and wind. Seasons, another atmospheric phenomenon, arise from Earth's axial tilt as it orbits the sun. This tilt results in varying solar angles and daylight hours, influencing temperature and weather patterns. For instance, during equinoxes, the sun's rays strike the equator directly, creating equal day and night lengths worldwide. Conversely, during solstices, the sun's rays are most direct at the tropics of Cancer or Capricorn, marking the longest and shortest days of the year. Natural hazards, including earthquakes, hurricanes, and tornadoes, further underscore the interconnectedness of Earth's systems. Earthquakes originate from the sudden release of energy caused by the sudden breaking of rocks along faults, generating seismic waves that propagate through Earth's layers. These waves provide insights into Earth's interior, revealing that S-waves travel only through solids, confirming the liquid state of the outer core. The point on Earth's surface directly above an earthquake's focus is called the epicenter. It is the location where the effects of an earthquake are typically felt most strongly, as it is directly aligned with the origin of seismic activity below the surface. Understanding the epicenter's location helps scientists assess the earthquake's potential impact and direct emergency response efforts effectively. Hurricanes, fueled by warm ocean waters, demonstrate the interplay between the atmosphere and hydrosphere, while tornadoes highlight the role of contrasting air masses in weather phenomena. Through its study of Earth's physical characteristics, processes, and systems, Earth science illuminates the planet's complexity and resilience. From the minute interactions within the biosphere to the grand dynamics of plate tectonics, Earth science reveals the mechanisms that shape our world. By fostering a deeper understanding of these processes, we gain the knowledge necessary to address environmental challenges, harness Earth's resources responsibly, and ensure a sustainable future. This integrative approach exemplifies the profound significance of Earth science in unraveling the mysteries of our ever-changing planet. Unit 2. Matter and Minerals. Minerals are the building blocks of rocks and are fundamental to Earth's structure and processes. Their unique compositions, properties, and roles in geological processes make them a cornerstone of Earth science. Understanding minerals begins with distinguishing them from rocks. While rocks are aggregates of one or more minerals, minerals themselves are naturally occurring, inorganic solids with a specific chemical composition and crystalline structure. This distinction forms the basis for examining minerals in greater depth, from their atomic makeup to their properties and classifications. At the atomic level, minerals are defined by their chemical and structural integrity. Atoms, the smallest units of matter, consist of protons, neutrons, and electrons. The atomic number of an element, which identifies it, corresponds to the number of protons in its nucleus. For instance, an element with an atomic number of 6 has 6 protons. The mass number, the sum of protons and neutrons, provides further detail about the atom. If the mass number is 13 for an atom with an atomic number of 6, the atom has 7 neutrons. These atomic variations give rise to isotopes, which are atoms of the same element with differing numbers of neutrons but the same number of protons. Isotopes play significant roles in radiometric dating, enabling scientists to determine the ages of rocks and minerals. Minerals are distinguished from other substances by specific properties that arise from their atomic structure. One critical property is hardness, which is tested by scratching a mineral on a surface or using another material to scratch it. This property reflects the strength of the atomic bonds within the mineral. Color, though commonly associated with minerals, is among the least reliable diagnostic properties due to its variability. For example, impurities can cause significant color changes within the same mineral species, making it an inconsistent identifier. Minerals are also classified based on their density, which reflects their specific gravity. Specific gravity is a measure of how much heavier a mineral is compared to an equal volume of water. For example, a cubic centimeter of quartz weighs 2.5 grams, olivine weighs 3.0 grams, and gold weighs a staggering 19.8 grams. This significant difference indicates that gold has a much higher specific gravity than quartz and olivine, a characteristic that has made it highly sought after throughout history. Gold's high density and luster also contribute to its use in jewelry and industrial applications, emphasizing the practical importance of understanding mineral properties. The crystalline structure of minerals further differentiates them. This structure is a result of the specific arrangement of atoms within the mineral. For example, quartz, a common mineral composed of silicon and oxygen, forms a distinctive crystalline lattice. Quartz is one of the most abundant minerals in Earth's crust and often dominates rocks that contain a high percentage of silicon and oxygen. Its durability and resistance to weathering make it a key component of many geological processes and a critical resource in industries ranging from glassmaking to electronics. The definition of a mineral also excludes certain materials commonly mistaken for them. Minerals must be solid, naturally occurring, and have a crystalline structure. This criterion excludes substances like coal, which, although naturally occurring and solid, is organic in origin and lacks a crystalline structure. This distinction helps clarify what constitutes a mineral and guides geologists in their studies of Earth's materials. The study of minerals extends beyond their physical properties to their chemical and elemental makeup. A fundamental rule is that atoms in a neutral state have equal numbers of protons and electrons. This balance maintains the electrical neutrality of the mineral structure. Understanding these basic atomic principles allows scientists to delve deeper into the formation and behavior of minerals under various environmental conditions. Minerals are broadly classified into silicate and non-silicate groups. Silicates, composed of silicon and oxygen, are the most abundant group, forming the backbone of Earth's crust. Quartz, feldspar, and mica are examples of silicate minerals, each with unique properties and roles in geological processes. Non-silicate minerals, which include oxides, sulfides, and carbonates, are less abundant but equally significant. For example, carbonates like calcite play a critical role in the carbon cycle and are central to the formation of sedimentary rocks. The practical significance of minerals cannot be overstated. They are the source of most of the raw materials used in construction, technology, and manufacturing. From the iron used to build skyscrapers to the rare earth elements essential for modern electronics, minerals form the foundation of modern society. Understanding their properties, formation, and distribution is therefore crucial not only for scientific purposes, but also for economic and industrial development. In identifying minerals, scientists rely on a combination of properties and tests. Hardness, luster, streak, and cleavage are commonly used criteria. For instance, hardness tests can distinguish quartz from softer minerals like calcite. Streak tests, which involve rubbing a mineral on a porcelain plate, reveal the color of its powdered form, providing another diagnostic clue. Cleavage, the tendency of a mineral to break along specific planes, also aids identification. These properties, taken together, form a systematic approach to mineral identification, ensuring accuracy and consistency in classification. The study of minerals also sheds light on the formation and evolution of Earth's crust. By examining mineral resources, reserves, and ores, geologists can trace the processes that concentrate valuable materials into economically viable deposits. For instance, the formation of gold deposits involves complex geological processes that concentrate the metal in specific locations. These deposits, often found in veins or placer deposits, have driven exploration and economic activity for centuries. Understanding minerals also involves recognizing their limitations and variability. For instance, two minerals may share several properties, such as luster or hardness, but differ in other characteristics like chemical composition. This variability underscores the importance of using multiple criteria when identifying minerals. For example, while color is often the most noticeable property, it is also the least reliable. A mineral like fluorite can appear in a wide range of colors, from purple to green to yellow, depending on impurities and structural variations. The integration of mineral studies with broader geological sciences enhances our understanding of Earth's history and processes. For example, isotopic analysis of minerals provides critical insights into the timing and rates of geological events. Radioactive isotopes, such as those found in uranium minerals, decay at known rates, allowing scientists to date rocks and reconstruct Earth's history with remarkable precision. This capability has revolutionized our understanding of events like the formation of the continents and the evolution of life on Earth. Minerals also play a pivotal role in understanding environmental and ecological systems. For instance, the weathering of silicate minerals regulates carbon dioxide levels in the atmosphere over geological timescales, influencing global climate. Similarly, the study of mineral deposits and their extraction has direct implications for environmental sustainability. Responsible mining practices, informed by a deep understanding of mineralogy, are essential for minimizing environmental impact and ensuring the long-term availability of critical resources. Unit 3. Rocks and minerals, weathering, soil, and mass wasting. Rocks, minerals, weathering, soil, and mass wasting form the foundation of Earth's dynamic geological systems. These components interact through natural processes to shape landscapes, influence ecosystems, and create the resources we rely on daily. The study of these interconnected phenomena reveals the complexity of Earth's surface and the forces that have sculpted it over billions of years. Rocks classified into igneous, sedimentary, and metamorphic types embody Earth's geological history, each reflecting specific conditions and processes. Sedimentary rocks, for instance, are formed through the compaction and lithification of sediments. Sand, when compacted and cemented together over time, forms sedimentary rocks, a category that includes sandstone and shale. These rocks often contain layers that provide a historical record of Earth's surface conditions, capturing information about ancient environments. One particularly interesting sedimentary rock, coal, forms from the accumulation of plant material in swampy environments. Over millions of years, pressure and heat transform the organic matter into this vital energy resource, showcasing how sedimentary processes extend beyond inorganic materials to include organic components. Igneous rocks, on the other hand, are born from molten magma. When magma cools and solidifies either below or above the Earth's surface, it forms igneous rocks. Plutonic rocks, such as granite, cool slowly beneath the surface, resulting in coarse-grained textures. Similarly, gabbro, another intrusive igneous rock, shares a texture similar to granite due to its slow cooling process. These rocks, found in the deep crust or exposed through erosion, provide a glimpse into Earth's internal activity. Volcanic rocks, such as basalt, form when magma cools rapidly at the surface, resulting in a fine-grained or glassy texture. Metamorphic rocks, the third major category, form through the transformation of existing rocks under heat and pressure without melting. For example, limestone, a sedimentary rock, undergoes metamorphism to become marble, a denser and more crystalline material valued for its use in art and architecture. This transformation exemplifies how geological processes recycle and reshape materials. Large-scale tectonic forces, such as those at convergent plate boundaries, drive regional metamorphism, where extensive pressure and heat alter vast stretches of Earth's crust. These processes demonstrate the dynamic nature of Earth's lithosphere and its continual evolution. Weathering, soil formation, and erosion are external processes that act on rocks, breaking them down and transporting their components. Weathering, classified as either mechanical or chemical, is the initial step in transforming rocks into soil and sediments. Mechanical weathering physically breaks rocks into smaller pieces without altering their chemical composition. Processes like frost wedging, where water enters cracks, freezes, and expands, illustrate how temperature changes contribute to rock fragmentation. In contrast, chemical weathering involves the breakdown of minerals through chemical reactions, such as oxidation or dissolution, altering their composition and forming new materials. The rates of weathering depend on factors like climate, rock type, and exposure, with warm, humid climates favoring chemical weathering and colder regions experiencing more mechanical weathering. Erosion, the next step after weathering, transports these particles through agents like water, wind, ice, and gravity. Rivers, for example, erode landscapes, carving valleys and depositing sediments downstream, eventually forming features like deltas. These depositional environments not only shape landforms, but also serve as reservoirs of nutrients and habitats for diverse ecosystems. The movement of sediments through erosion connects Earth's surface processes with its hydrological and ecological systems, creating a dynamic interplay that sustains life and shapes landscapes. Soil, a product of weathering and organic activity, is a critical component of Earth's surface. Its composition, texture, and structure vary depending on the parent material, climate, topography, biological activity, and time. These factors influence soil development and classification, affecting its fertility and ability to support plant life. Soils form in layers or horizons, each representing a stage in its development. The topsoil, rich in organic matter, is particularly vital for agriculture and vegetation. However, soil is also susceptible to erosion, especially in regions with steep slopes or intense agricultural activity. Sustainable land management practices are essential to minimize soil loss and maintain its productivity. Mass wasting, a natural process where gravity moves soil, rock, and debris downslope, plays a significant role in shaping landforms. It includes events like landslides, rockfalls, and creep, each triggered by factors such as water saturation, vegetation removal, earthquakes, or human activity. Mass wasting not only alters landscapes but also poses risks to human settlements and infrastructure. Understanding its triggers and impacts is vital for mitigating hazards and planning safe development. These geological processes are interconnected, demonstrating the complexity and dynamism of Earth's systems. Rocks, for instance, undergo a continuous cycle known as the rock cycle, transforming between igneous, sedimentary, and metamorphic states. Magma from Earth's mantle cools to form igneous rocks, which are then weathered and eroded into sediments. These sediments, through compaction and lithification, form sedimentary rocks, which can later undergo metamorphism under heat and pressure. This cycle illustrates the recycling of materials within Earth's crust, driven by both internal and external forces. The study of rocks and their transformations provides valuable insights into Earth's history. For example, sedimentary layers preserve fossils, revealing information about past life and environments. Metamorphic rocks record the pressures and temperatures experienced during tectonic events, offering clues about mountain building and plate movements. Igneous rocks, meanwhile, provide evidence of volcanic activity and the composition of Earth's interior. In addition to their scientific significance, rocks and minerals are essential resources for human society. From building materials like limestone and marble to energy sources like coal, these materials underpin modern infrastructure and industry. The study of geological processes not only helps locate and extract these resources, but also informs sustainable practices to minimize environmental impact. Weathering and erosion also influence human activity by shaping landscapes and affecting soil fertility. Understanding these processes allows for better land management, ensuring agricultural productivity and mitigating the impacts of natural hazards. For example, measures like planting vegetation on slopes or constructing terraces can reduce soil erosion, preserving the integrity of the land and preventing downstream sedimentation. Mass wasting highlights the importance of integrating geological knowledge into urban planning and disaster management. Identifying areas prone to landslides and implementing preventative measures can save lives and protect property. As human populations expand into mountainous and unstable regions, the need for such expertise becomes increasingly critical. The interplay between geological processes and human activity underscores the relevance of earth science in addressing global challenges. From managing natural resources to mitigating the impacts of climate change and natural disasters, the study of rocks, weathering, soil, and mass wasting equips us with the tools to navigate a rapidly changing world. By understanding these processes, we can better appreciate the forces that shape our planet and develop strategies to live sustainably within its boundaries.